Jan 2013, question 5. Here we've got a question with percentage yield, bond enthalpy calculations, and a bit of polymers. It's a real mixture, this question. I've started off by putting in the MRs that you will need. So we've got chloroethene, and the formula is made from 1,2-dichloroethane. A chemical plant uses 19.8 tons of dichloroethane. So we're starting off with 19.8 tons of this, and it makes 11.25 tons of chloroethene. So this is what is actually made. So this is our act mass. Now what we need to do first of all is calculate, theoretically, if I have a particular number of moles of this, ratio of 1 to 1, I should make a particular number of moles of that. So my first job is to calculate the number of moles here. I've got the MR, I've got the mass. So N equals M over MR. We've got 19.8 times 10 to the 6 over 99, which gives 2 times 10 to the 5. So that's the number of moles I've got of 1,2-dichloroethane. It means that theoretically that's the same number of moles, as it's a 1-to-1 ratio, that I will get of chloroethene. So I can say that my ratio is 1 to 1. So the number of moles of CH2 CHCl, which is my chloroethene, is also equal to 2 times 10 to the 5. If I times that by the MR, so moles times MR, so 2 times 10 to the 5 times 62.5, which I calculated already up there, I get 1.25 times 10 to the 7. Now that is the mass in grams at the minute, 10 to the 7, of what I would get theoretically here. What I now need to do is take my actual and divide it by my theoretical. So my percentage yield is my act over my theo is equal to 11.25, I'll put it in grams now, times 10 to the 6 over 1.25 times 10 to the 7. Notice if you look at this, it's essentially, if I cancel down, I've got 11.25 over 12.5. Now I've got to times that by 100 to give me a percentage, and that equals 90%. So I've been through, I've worked out the number of moles that I've started with from my 19.8. Then I used the ratio to work out the number of moles theoretically that I would get of chloroethene. Using the MR of chloroethene, I've worked out then theoretical mass that I've got here. In the question it gave me an actual mass. So I did actual divided by theoretical, and I got 90%. Part B, bond enthalpy calculation. It is crucial in these questions, because they're quite nice questions, but it is crucial that you draw out the full displayed formula for the reactants and the products, because that way you can go through counting the bonds. So on the reactant side, you've got the bonds that are being broken. You've got, to start with, CH bonds. 1, 2, 3, 4. 4 times the value of the CH bond. 4, 1, 3. Notice how these are all positive. It's all bond enthalpy. It's the amount of energy required to break a bond. And so you're putting energy in. It's being absorbed. It's endothermic. Then CCl bonds. 1, 2. 2 times 3, 4, 6. Didn't want that to happen. I'm just going to pretend that it didn't. Then I've got the CC bond. I've lost my cursor. That's the trouble when it does that. Here we go. No, it's not going to let me do that. I've got my CC bond, which I've just got one of them. And in this case, then I've got 3, 4, 7. Now, if you can still make head or tail of that, that's 4 times 4, 1, 3, 2 times 3, 4, 6, and 4, 3, 4, 7. Adding all that up together, I make it 2, 6, 9, 1. On the other side, bonds made or formed, we've got 1, 2, 3 CH bonds, so CH again, 3 times 4, 1, 3. I've got 1 C double bond C, which is 612. I've got CCl bond, and I've got one of those, 346, and I've got an HCl bond, which is 432. In total that, and this isn't the answer though, it's in the place of the answer, in total that I make as 2, 6, 2, 9. Then all I've got to do is take this number from this number, so I've got 2691 minus 2629, and it gives me an answer of plus, bond enthalpies are always positive, the results 62. In fact, I'm talking rubbish. They're not always positive. If the bonds broken is greater than the enthalpy of the bonds made, then obviously it would be endothermic. If it was the other way around, it would be exothermic. So the result, the answer, is very important that you put the plus or the minus sign to show you know whether it's going to be an exothermic or an endothermic reaction. All bond enthalpy values will be positive, so my apologies there. For part C then, we're asked to draw an equation of the polymer to PVC. So using displayed formula, you've got to draw the reaction from its monomer. So we've got chloroethene, C double bond C, I'll draw them up like this time, Cl, H, 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 monomer, I want, importantly, to put in that the number I've got of them, N monomers. That will give me my polymer C. I'll break the double bond, so I just have a single bond there. I have exactly the same groups. I've got my Cl, my H, my H there. I've given it wings, square brackets around, and do not forget, so it's going to be worth one of your marks here, N. So you'll get 1 mark for the monomer, 1 mark for the polymer, and 1 mark for balancing with your N. Then it goes on to ask, disposal of polymers can be done by combustion. Problem with PVC is that you've got HCl. How can that HCl be removed? And you've got here something you could suggest, like, well, it's an acidic gas, react with, alkali, e.g., give them an example, NaOH, and that's your 1 mark. Then, what is polymers? State 2 ways other than landfill and combustion. It's important you read the question here because people fall into that trap. It does say other than landfill and combustion, so don't mention them in your answer. Here we are, landfill and combustion. Don't mention, here we go, it's going crazy, my highlighter now. Don't mention landfill or combustion. So what can I mention? I've lost my cursor completely, as usual. Hold on a second. Okay, so don't mention landfill and combustion. You've got then, importantly, so hopefully this is still recorded. I'm just going to tell you in a minute if it doesn't work. Landfill and combustion, but don't mention them. So what you can mention, sort and recycle. And secondly, you've got a couple of options here. You could say cracking, and essentially the cracking is to produce organic feedstock, which is the key one really. So use as organic feedstock I'm going to have. There are other things you can mention. You could say mainly that cracking to produce organic feedstock, which is what happens. You could also say use for the production of organic compounds. But I think where people go wrong is they think they've got it, but they don't put sort and recycle. You just put recycle, which won't get you the mark. So sort and recycle, use as organic feedstock. Finally then, give an example of a type of polymer being used to minimize environmental damage. In this case, you could be specific and name one, but it doesn't actually ask you to name one here. It just says a type of polymer, and so you'd want to go for biodegradable. You could also have compostable or photodegradable, but I think the key thing there for a type of polymer being developed, it doesn't say name, so here we've got biodegradable. If you did have to name one, then you've got things like polylactic acid or just simply starch, but here biodegradable is key.